Swayam Prabha. Digital India. Educated India.
Moving on to combinations, here the objects we are going to count is something we already are familiar with, namely the subsets. So the combinatorial question is, how many subsets of size k does a set of size n have? Okay. Now you could think of these this also as a question about strings, because we could represent subsets as strings without repetitions. For instance, if my alphabet is A, B, C, D, E, and I'm talking about a subset A, C, D, you could think of it as just a string A, C, D. Okay? But one problem is that this representation is not unique. The same subset A, C, D could be represented using multiple strings like ADC or CAD. So these are strings without repetition, but there are, the order is different, right? However, we actually know, so there is double counting now, there's multiple counting now, but we actually know how much we are, how many times we are counting each subset. So a subset can be represented, say in this case a subset of size 3, can be represented in exactly 3 factorial ways. Right, so or more generally a subset of length k, which we represented as a length k string. Well, it's not just one length k string, there will be k factorial permutations of that string which all correspond to the same subset. So there are k factorial strings whose they are strings without repetitions. They all use the same subset of size k as their as the characters they contain, and there are k factorial of them. Now, so what we are interested in is counting the number of subsets, but we could actually first count the number of strings, number of repetition-free strings of length k, and then we know that each subset has k factorial copies of itself among these strings of length k. So just scale down this count by a factor of k factorial, because every subset appears exactly as k factorial strings without repetitions. You can count the strings without repetitions and then divide that count by k factorial. So that is to say, Cnk is simply Pnk divided by k factorial, and if you plug in the expression for Pnk, this is what you get: n factorial divided by n minus k factorial times k factorial. Okay, so that is a very important quantity, the Cnk, and let me say a few more things about Cnk, but the derivation is simply a consequence of what we already saw for Pnk, and the fact that again this is a consequence of Pkk being k factorial. Okay, so this, by the way, Cnk is how I would write it in the slides, but more often you would encounter it using this notation, which you can read as n choose k. So there's a number of ways in which you can choose a subset of k from a set of size. So this quantity n choose k is quite important. Let's spend some time trying to get a better sense of this quantity. So this is the expression here, the formula for Cnk. But you may get a better sense of how it behaves by looking at a plot like this. So I plotted C10k for various values of k equal to 0 to 10. So beyond k equal to 10, this is 0. Right? You cannot choose a subset of size k from a set of size n if k is greater than n. And as you can see here, C10 10, 0 is 1, so this corresponds to the empty subset. C 10, 1 is 10, this corresponds to there being 10 singleton sets, and so forth. And as C and K keeps increasing until it peaks and starts decreasing. In fact, you might observe a certain symmetry in this plot, and that's because C and K is equal to C and n minus K. That's something you can see once you look at the formula here. If you substitute, instead of K, you substitute n minus K, then you'll get back the same formula as C and K. Right, so C and K equals C and n minus K. But not just from the formula, you can also think of it more intuitively from the definition or from the meaning of C and K, namely the number of subsets of size K. Whenever you're choosing a subset of size K, you're also choosing its complement of size n minus K. So the number of ways of choosing a subset of size K is exactly the same as the number of ways of choosing complements of size n minus K. Complements are also just simply subsets. So C and K and C and n minus K are counting the same thing. Number of ways of partitioning your set into a subset of size n and the remaining n minus K elements. As I already pointed out, C 10, 0 is 1 because it's just counting the number of empty subsets of a set. And C 10, 10 is also 1. It's counting the number of subsets which are the entire set. And there's just one of that, the entire set. So that is C and n. That's for n equal to 10 or positive integer. What about C00? How should we define C00? Well, it's supposed to count the number of empty subsets of the empty subset, and indeed there is one such subset, namely the empty subset itself. Right? So C00 should be 1. And you would get that from our formula as well. So this will become 0 factorial divided by 0 factorial times 0 factorial. Another interesting thing to notice about C and K is that if I summed up C and K over all K, so I fix an n and sum up C and K over all K from 0, 1, 2, 3 all the way up to n. So in this picture, I sum up the heights of all these bars. What I would get is 2 to the n. And why is that? Because C and K is counting the subsets of size K. By summing up over all K, I am counting the total number of subsets, right? And the total number of subsets of a set of size n is 2 to the n. This includes the empty set and the complete set, right? If you sum all of them, sum the counts of all sets of different sizes, you'll get the count of all subsets, and that's 2 to the n. Okay, that actually is a special case of something even more general. I can say 1 plus x to the power n for any value x, or you could think of it as a formal variable, is actually this polynomial here. It's a summation of x to the k, x to the power k, multiplied by this coefficient c and k. Again, summation is over all values of k for which c and k is not 0. So k equal to 0 to n. Okay. And why do I say it's a more general expression than what we just saw? If I put x equal to 1, then this x to the k just disappears. It's just 1. So this is just summing up c and k. And on this side, I get it as 1 plus 1 to the power n, which is 2 to the power n. Okay. So why does this hold? Let's see an example here. I take n equal to 3. I compute 1 plus x the whole cube, and I've just written it out, just using distributive property. So first I multiplied 1 plus x, the green 1 plus x with the yellow 1 plus x. I color coded them so that you can see in the when I'm opening the brackets where the different terms are coming from. So the green 1 times the yellow 1 is this one, then there's a green 1 times the yellow x, and so forth. So there are 4 such combinations, and then I also open the brackets of this pink expression and I get 8 such terms, right? So the 8 terms simply correspond to terms of this form. I pick either 1 or x from the yellow factor, so from the pink factor, 1 or x from the green factor, and 1 or x from the yellow factor. Okay, so there are 2 times 2 times 2 ways of doing this. So there are 8 of these terms. And what I'm interested in is the coefficient of x to the power k, which is to say how many of these things have exactly k x's and n minus k ones. Okay, so the coefficient of x to the power k is the number of strings of the form, strings which consist of which are over the alphabet 1 and x, right? And it should have exactly k x's in it. That is simply choosing k positions out of n positions to be to be x, and there are c and k ways of doing that. Okay. So the coefficient of x to the power k in here, I hope I convinced you, is c and k. If you're not fully convinced, you can prove this by induction, and what you would need to do is, just to describe where the inductive step, you'll be considering 1 plus x times 1 plus x to the n minus 1, and 1 plus x to the n minus 1 you would have expanded using the inductive hypothesis. So all these a and b are coming from the expansion from the inductive hypothesis. What is the coefficient of x to the k? You will get a contribution from b times x to the k times 1, another from x times a times x to the k minus 1. So that's a times x to the k. So there's an a times x to the k and a b times x to the k in this expansion here. So the coefficient is a plus b. And what is a and b? From the inductive hypothesis, a would be, so these are both coefficients in the expansion of 1 plus x to the n minus 1. So a is a coefficient of x to the k minus 1, so that coefficient is by inductive hypothesis c n minus 1 comma k minus 1, whereas b is c n minus 1 comma k. So what remains to be done is to say that, okay, if you add this a and b up, you would get c and k. So you'll get n choose k. You can do that by substituting the expression in terms of factorials, or you can also do that very directly from the meaning of c and k, that it's counting the number of subsets of size k. So to see that, take an element in the set, the set of size n, and let's designate it as a special element a, and all the subsets can be classified into two kinds: subsets which include the special element and those that do not include the special element. And how many subsets include the element a, subsets of size k, right? How many of them include the element a? Well, they need to have a, and then they need to have k minus 1 more elements chosen from the remaining n minus 1 elements. So there are c n minus 1 comma k minus 1 ways of doing that. And how many do not include a? So you need to choose all k elements from n minus 1 elements excluding a, so that is this number. Okay, so that's an intuitive way to quickly see that this identity holds. In fact, this identity could have been used as a definition of c and k, or instead of the expression we had in terms of n factorial. You could also have written this down and use that as a definition. To be a definition, you have to make sure it uniquely defines a value. It's not just some property of C and K. And in particular, you need some base cases. So here's my table of all values of C and K. And the base cases I've chosen are these two, C n0 and C n n. Right? The number of empty subsets and the number of full subsets. In all cases, it is 1. And the idea is that once you fill in these ones in this table, then any other element in this table can be computed using this expression. And I would leave it to you to convince yourself. So what this expression is saying is that, say you take this number 10 here, C5 2 is a sum of C4 1 and C4 2. So you look at the element right above it, the cell right above it, and the cell to the above and left of it, and whatever values there are, you sum them up, you will get the value here. This is also called the Pascal's triangle sometimes. So that's just an illustration of this formula here. And the important thing is that once you fix these base cases, you could start with an empty table and start filling in values in each of these cells. If you look at the two cells above, if one of them is empty, you keep trying to fill that by going above and to the left. And since the left end and this diagonal are fully filled, you will never have to go outside of this region, and every element can get filled in. Okay, we will talk about recursive definitions more formally later, but for now this is something for you to remember. In fact, you could use this formula here also to prove this identity here also to prove the formula for C and K. And here I excluded all the part in this table where K is strictly greater than N, but an alternate base case I could choose is here for K positive number, K equal to 1, 2, 3, so forth, and N equals 0. So these are non-empty subsets of the empty set, and the number of such subsets are 0. So I could set that as a base case, and I encourage you to see what happens in this table. If I use those as base cases, I'll still get exactly these entries here. All right, the last thing I want to do, this came up a couple of times. We have been using, we talked about strings of length K, but we have also been talking about K equal to 0, and we talked about an alphabet of size N, and in defining C and K, we have been talking about N equal to 0. So let me just collect all the conventions about N equal to 0 and K equal to 0 here. So remember, we talked about the length K strings over an alphabet of size N being equal to N to the K. So what happens when K equals 0? So we are talking about strings of 0 length. That may not make much sense, but we could just define that there is an empty string. Okay, so it's a valid string. It is a length 0 string. There's only one such string, the empty string. And once you have the empty string, then the number of length 0 strings over an alphabet of any size N is indeed N to the 0, because N to the 0 equal to 1. That works for all N greater than 0. What should we do for N equal to 0? Well, we are going to just define this count, so 0 to the power 0 may not make sense, but in terms of counting the number of length 0 strings over an empty alphabet, over an empty alphabet you cannot define any strings of any length, except you can define the empty string if you want to. So we will allow that there is an empty string that is defined over the empty alphabet. So this count here is again 1. The empty string is a valid permutation in the sense that there are no repeating symbols. So that justifies our so pn0 we would take as 1, and that fits in with our formula for p and k. So if you put k equal to 0, p n factor, you get n factorial divided by n factorial, which is 1. So this convention fits in with this formula. What should p00 be? Again, there is one string, the empty string, and we allowed it to be called a permutation. So p00 should also be 1, and the formula again fits that because this will be 0 factorial divided by 0 factorial, and that we already talked about this, the size 0 subsets of size n set. So Cn0 is 1, and again the formula fits that, and similarly C00, again the formula fits. So all of this, once you have n factorial equal to 0, and since we do have that even for defining p and n, we needed n factorial for this formula to hold, then the formula actually extends to p and k and c and k, and the number of k length strings of over an alphabet of size n for n equal to 0 and k equal to 0. Okay, so that's all I want to tell you about permutations and combinations for now, and we will continue with counting more things in the next lecture.